The signals are cut, the noise has faded. Welcome back to the Silence of the Black series. Today we walk together once more in the deepest corners of the universe, chasing the unknown. A new secret in every video, a moment of peace in every second. Don't forget to subscribe to stay with me on this journey. Take a deep breath. We are beginning. You stand at the edge of the day, watching as the sun begins its slow descent toward the horizon. The light around you is changing, softening, taking on qualities that were absent just hours ago. What you are about to witness is not merely a sunset, but a demonstration of one of nature's most elegant physical principles: atmospheric refraction. The sun appears to be sitting on the horizon, a perfect orange disk ready to disappear behind the distant line where Earth meets sky. But this is an illusion, a trick of light that has fooled human eyes for millions of years. The real sun has already set. What you are seeing is a ghost, an image created by the bending of light as it passes through Earth's atmosphere. The sun that you watch sink below the horizon left its position in the sky more than 2 minutes ago, but the light from that moment is only now reaching your eyes, bent and distorted by the very air you breathe. To understand this phenomenon, you must first understand how light behaves when it moves through different mediums. Light travels at different speeds through different substances. In the vacuum of space, it moves at its maximum velocity, approximately 300,000 kilometers per second. This is the speed limit of the universe, the fastest anything can possibly travel. But when light enters a transparent medium like air, water, or glass, it slows down. The denser the medium, the slower light moves through it. When light passes from one medium to another at an angle, this change in speed causes it to bend. Imagine a car driving from a smooth road into a patch of deep mud. If the car hits the mud at an angle, the wheel that enters first will slow down while the other wheel continues at speed, causing the car to turn. Light does the same thing when it enters a denser medium at an angle. It bends. You can observe this refraction in everyday life. Place a straw in a glass of water and notice how it appears to bend at the surface. The straw is not actually bent. The light reflecting off the submerged portion is bent as it exits the water, creating the illusion of a break. The same principle applies to sunlight entering our atmosphere, though on a vastly larger scale. Earth's atmosphere is not uniform. It consists of layers of air with varying density, becoming progressively thinner as you move away from the surface. The lowest layer, the troposphere, is the densest, containing about 80% of the atmosphere's mass. Above it, the stratosphere is thinner still, and above that, the mesosphere and thermosphere fade gradually into the vacuum of space. When sunlight approaches Earth from space, it encounters this layered atmosphere at an angle. The light enters the thin upper atmosphere first, then passes through progressively denser layers as it descends. Each layer bends the light slightly more than the last, creating a cumulative effect that can significantly alter the apparent position of the sun. This bending is most dramatic when the sun is near the horizon. When the sun is high overhead, its light passes through the atmosphere at nearly a perpendicular angle, and the bending is minimal. But when the sun is low on the horizon, its light must travel through a much longer path through the atmosphere, passing through more layers at a shallower angle. The cumulative refraction can shift the apparent position of the sun by more than its own diameter. As you watch the sun approach the horizon, its light is passing through an atmospheric path more than 30 times longer than when it was directly overhead. This extended journey through the atmosphere amplifies the refraction effect dramatically. The light is bent so much that you can see the sun even after it has physically dropped below the horizon. At the moment of sunset, when the sun appears to touch the horizon, the real sun has already dipped below it by about the width of the sun itself. You are seeing a refracted image, a ghost of the sun, created by the gentle bending of light through the atmosphere. The sun has already said goodbye, but the atmosphere delivers its message a few minutes longer, stretching the day's end into a lingering farewell. This bending affects more than just the sun's position. It also distorts the shape of the sun's image. The bottom of the sun, where light passes through the densest atmosphere, is bent more than the top, where light travels through thinner air. This differential bending compresses the sun's image vertically, making it appear oval rather than round. The familiar flattened shape of the setting sun is a direct result of atmospheric refraction. You watch as the sun continues its apparent descent, its color deepening from yellow to orange to red. The refraction continues, bending the light, stretching the moment, giving you a few extra minutes of daylight that the sun has already left behind. The sun you see is not the sun of the present moment but the sun of 2 minutes ago, its light delayed by its journey through space and bent by its passage through the atmosphere. The effect is so pronounced that you can sometimes see the sun as a distorted oval, its bottom edge seemingly cut off or flattened against the horizon. In rare conditions, when temperature gradients create unusual density variations in the atmosphere, you might even see multiple images of the sun, a phenomenon called the Novaya Zemlya effect, named after the Arctic archipelago where it was first observed. This is the gentle science of atmospheric refraction. It is the reason we can see the sun for a few minutes after it has physically set, the reason its image is distorted and flattened, the reason we are granted a lingering farewell from our nearest star. It is a reminder that what we see is not always what is real, that our perception is shaped by the medium through which we observe the world. The sun dips lower and you know that what you are seeing is not real. But it feels real, looks real, and that is enough. The atmosphere has given you a gift. A few extra moments of light, a few extra moments of beauty, a few extra moments to say goodbye to the day. This gift is not unique to sunsets. Atmospheric refraction affects everything we see in the sky. Stars appear slightly higher than their true positions, especially near the horizon. The moon, like the sun, is flattened and distorted as it rises and sets. Even the planets, those wanderers of the night sky, have their positions shifted by the same atmospheric lens. The amount of refraction depends on atmospheric conditions. Temperature, pressure, and humidity all affect the density of air and therefore the amount of bending. On a warm evening with high pressure, the refraction may be minimal. On a cold night with temperature inversions, the bending can be dramatic, creating mirages and distorted images that seem to defy explanation. As the last sliver of the sun disappears, you understand that you have witnessed something remarkable. Not just a sunset, but a demonstration of the physics that shapes our perception of the world. The light bent, the image lifted, the moment extended, all by the gentle, invisible hand of atmospheric refraction. The sky begins its slow transition to darkness, but you carry with you the knowledge of what you have just seen. The ghost sun, the bent light, the lingering farewell. It is science, but it is also poetry. It is physics, but it is also beauty. The first stars appear, tiny points of light that will also be affected by refraction, though less dramatically. Their light too is bent as it enters the atmosphere, shifting their apparent positions slightly. Astronomers must account for this refraction when making precise measurements, calculating the exact amount of bending based on atmospheric conditions. Everything you see in the sky is a product of this bending, this gentle distortion, this atmospheric lens. You stand there at the edge of day and night and you understand, we never see things exactly as they are. We see them through the filter of our atmosphere, through the bending of light, through the physics that shapes our perception. And that is beautiful. The universe reveals itself to us not directly, but through the mediating influence of our own planet's embrace. The temperature is dropping now, the air cooling as the sun's warmth fades. You can feel the change just as you have seen the change in the light. The atmosphere that bent the sun's rays is the same atmosphere that holds the day's heat, that carries sounds to your ears, that fills your lungs with each breath. It is your medium, your home, your interface with the cosmos. The last traces of color fade from the western sky, and true darkness settles in. The stars shine more brightly now, their light having traveled years, centuries, millennia to reach you. Each photon has journeyed across vast distances, only to be bent at the last moment by the thin veil of atmosphere that surrounds your world. Each star you see is slightly displaced from its true position, a ghost like the sun you just watched set. You turn away from the horizon, carrying with you the memory of the bent light, the lingering sun, the gentle science that made it all possible. The day is over, but its lesson remains. Reality is not always what it appears, and sometimes the most beautiful truths are hidden in plain sight, waiting for a curious mind to uncover them. The night surrounds you now, dark and cool and full of stars. Somewhere beyond the horizon, the sun continues its journey, invisible but present, its light still traveling, still bending, still reaching toward worlds unseen. And you, standing on your small planet, have witnessed a small piece of the grand cosmic dance. This is atmospheric refraction. This is the bending of lingering light. This is the gentle science that gives us sunsets. You stand at the threshold of evening, watching as the sky begins its slow transformation from the bright blue of day to the rich palette of sunset. The sun has not yet reached the horizon, but already the quality of light is changing. The blue that dominated the sky just an hour ago is fading, thinning, giving way to something new. This is not merely the approach of night. It is the physical manifestation of one of nature's most elegant phenomena, Rayleigh scattering. To understand why the sky changes color at sunset, you must first understand why it is blue during the day. Sunlight appears white to our eyes, but it is actually composed of all the colors of the rainbow. When this white light enters Earth's atmosphere, it encounters the molecules of air, primarily nitrogen and oxygen, that surround our planet. These molecules are tiny, much smaller than the wavelength of visible light, and they interact with different colors in different ways. The interaction depends on the wavelength of the light. Blue light has a short wavelength, while red light has a long wavelength. When sunlight strikes an air molecule, the short wavelengths are scattered much more efficiently than the long ones. In fact, blue light is scattered about 10 times more than red light. This preferential scattering is called Rayleigh scattering, named after the British physicist Lord Rayleigh, who first described it in the 19th century. During the day, when the sun is high overhead, the light travels through a relatively thin layer of atmosphere to reach your eyes. The blue light is scattered in all directions by air molecules, filling the sky with blue light no matter which direction you look. The red and orange light, with their longer wavelengths, pass through the atmosphere with less scattering, continuing in straight lines toward the ground. This is why the sky appears blue and the sun appears yellowish-white. But as the sun approaches the horizon, everything changes. The light must now travel through a much longer path through the atmosphere to reach your eyes. Instead of passing through a few miles of air, the sunset light must traverse 100 miles or more of increasingly dense atmosphere. This extended journey amplifies the effects of scattering dramatically. You watch as the sun sinks lower, its light passing through more and more atmosphere. The blue light, already the most easily scattered, is now scattered so thoroughly that it is removed almost completely from the direct path to your eyes. It bounces from molecule to molecule, diffusing throughout the sky, becoming so diffuse that it no longer contributes to the direct sunlight reaching you. This removal of blue light is the first step in the creation of a sunset. As the blue is scattered away, the remaining light becomes progressively richer in the longer wavelengths, the greens, yellows, oranges, and reds. The sun itself begins to change color, shifting from white to yellow to orange as more and more of the blue is stripped away. The process is gradual at first, almost imperceptible. The sky overhead remains blue, though a deeper blue than before. But near the horizon, where the light path is longest, the changes are more dramatic. The sky takes on a golden hue, then orange, then the first hints of red. You look toward the sun and see that its disk has become a deep orange, comfortable to look at now where it would have been blinding just hours ago. The blue light that once dominated its color has been scattered away, leaving only the warmer tones behind. The sun appears larger than it did at noon, though this is an illusion created by comparison with the horizon. But its color is real, a direct result of the scattering of shorter wavelengths. The sky around the sun is painted in gradients of color. Nearest the sun, where the light path is shortest through the atmosphere, the colors are lighter, yellows and pale oranges. Farther from the sun, where the light must travel through even more atmosphere, the colors deepen into rich oranges and reds. And at the zenith, directly overhead, the sky remains blue, though a deeper, more saturated blue than the bright azure of midday. This gradient of color is a map of the atmosphere itself. Each color tells you how much air the light has passed through to reach your eyes. The red light near the horizon has traveled through the most atmosphere, losing all its blue along the way. The blue light overhead has traveled through the least, retaining its original color. You watch as the colors continue to deepen. The sun touches the horizon, and now the light is passing through its longest path yet. The blue is long gone, scattered into invisibility. Even some of the green and yellow are beginning to fade, leaving behind the oranges and reds that are least affected by scattering. The sky itself is changing now. The blue overhead is darkening, becoming the deep violet of twilight. This is another effect of scattering. As the sun sets, the light illuminating the upper atmosphere comes from below the horizon, passing through even more atmosphere to reach those heights. The blue is scattered away there too, leaving behind the longer wavelengths that create the deep purples and violets of the evening sky. You think about the journey these photons have made. Each particle of light left the sun 8 minutes ago, traveling at 300,000 kilometers per second across the void of space. Then it encountered Earth's atmosphere and began its slow, tortuous path through miles of air, bouncing and scattering, losing its shorter wavelengths along the way. By the time it reaches your eyes, it is a survivor, a photon that has shed its blue companions to become pure orange or red. The scattering that creates these colors is not just a visual phenomenon. It has practical implications as well. Pilots and sailors have long used the colors of the sky to predict weather. A red sky at night, the saying goes, is a sailor's delight, indicating high pressure and stable air. A red sky in morning is a sailor's warning, suggesting that a storm system is approaching. These traditional weather sayings have a basis in the physics of scattering, as the colors reveal the amount of moisture and dust in the atmosphere. The dust and pollution in the air can enhance the sunset colors. Particles larger than air molecules, such as those from volcanic eruptions or forest fires, scatter light differently, creating even more dramatic displays. This is why the most spectacular sunsets often follow volcanic eruptions, when the stratosphere is filled with fine ash that scatters and refracts light in complex ways. You watch as the last of the blue fades from the western sky, replaced by a deep orange that shades into purple at the zenith. The sun itself is half hidden now, its remaining light painting the clouds above it in shades of pink and magenta. The clouds act as screens, catching the colored light and reflecting it back to your eyes, amplifying the effect. The science of scattering explains all of this. The preferential scattering of short wavelengths, the longer path through the atmosphere at sunset, the removal of blue light leaving behind the warmer tones. Each aspect of the sunset is a direct consequence of these physical principles. What you are witnessing is not magic but physics, not art but nature, not mystery but understanding. And yet, understanding does not diminish the beauty. If anything, it enhances it. Knowing why the sky turns orange does not make it any less beautiful. It makes it more fascinating. The physics behind the sunset is itself a kind of poetry, an elegant description of how light and matter interact to create the world we see. The sun disappears below the horizon, but the show is not over. The colors linger, fading slowly as the last rays of sunlight pass through ever thicker layers of atmosphere. The western sky glows with an afterimage of the day, a final farewell from the sun that has already set. You stand there watching as the colors gradually fade to gray, then to the deep blue of true twilight. The scattering continues even after the sun is gone, as sunlight illuminates the upper atmosphere from below the horizon. The sky will continue to change for another hour, slowly transitioning to the black of night. The first stars appear, tiny points of light that have also been affected by scattering, though their light is too faint for the color change to be visible to your eyes. But the same physics applies. Starlight too is scattered by the atmosphere, which is why stars near the horizon appear to twinkle more than those overhead. The scattering causes slight variations in their brightness and color, creating the familiar twinkling effect. You think about the blue light that was scattered away. Those photons are not gone. They are simply going in different directions. Some have been scattered back into space, never reaching the ground. Others have been scattered multiple times, eventually reaching your eyes from directions other than the sun. This is why the sky is bright even when you look away from the sun. The scattered light fills the entire sky. The blue that dominated the day has now been replaced by the red of evening. The scattering that removed the blue has given you this gift of color, this final flourish of light before darkness falls. It is a reminder that even in loss there is beauty, that what is taken away can create something new and wonderful. As the last colors fade from the sky, you feel a sense of gratitude. You have witnessed the scattering of shorter blues, the transformation of white sunlight into the rich palette of sunset. You have seen physics in action, beauty in motion, the everyday miracle of light and air. The night deepens around you, but you carry the memory of the colors with you. The blues that scattered, the reds that remained, the sky that transformed before your eyes. This is the gentle science of scattering. This is why the setting sun paints the sky in vibrant colors. You stand at the peak of twilight, watching as the sky transforms into its most dramatic display. The blue has been scattered away, the oranges and yellows have come and gone, and now the deepest, richest colors are emerging. The western sky blazes with ambers and golds near the horizon, while above, deep violets and purples spread across the dome like a celestial curtain. This is the climax of the sunset, the moment when the surviving photons make their final, most beautiful statement. The colors you are witnessing now are the survivors. Of all the millions of photons that left the sun 8 minutes ago, only those with the longest wavelengths have made it through the atmospheric gauntlet. The blues and greens were scattered away earlier, their energy dissipated across the sky. The yellows and oranges have faded as the sun dropped lower. What remains are the reds, the deep oranges, and the violets, the most resilient colors in the spectrum. To understand why these particular colors dominate the final moments of sunset, you must consider the path length of the light. When the sun is on the horizon, its light is traveling through more than 30 times as much atmosphere as at noon. This extended journey through air molecules, dust particles, and water vapor acts as a filter, progressively removing shorter wavelengths and leaving only the longest. The red light that reaches you now has a wavelength of about 700 nanometers. This is nearly twice as long as the blue light that was scattered away hours ago. This longer wavelength means red light is much less likely to interact with air molecules. It slips through the atmosphere with minimal scattering, maintaining its direction and intensity even after traveling through 100 miles of air. The deep oranges and ambers have wavelengths between 600 and 650 nanometers. They too are relatively long, though not as long as pure red. They survive the atmospheric journey but are more affected by scattering than the reds, which is why they appear closer to the horizon where the light path is longest. The violets and purples are something of an exception. Violet light has a shorter wavelength than blue, around 400 nanometers, so it should scatter even more easily. Yet at sunset, we often see beautiful violet and purple hues in the sky. This seeming contradiction is resolved by understanding that the violet light we see is not direct sunlight, but rather light that has been scattered and then rescattered in complex ways. The purple colors of sunset come primarily from two sources. First, as the blue light is scattered away, it leaves behind a mixture of colors that can appear violet when combined with the reds and oranges. Second, some of the blue light that was scattered upward into the upper atmosphere is then scattered downward again, passing through the red-rich lower atmosphere and creating purple hues through a process called additive color mixing. You watch as these colors paint themselves across the sky. Near the horizon, where the sun has just disappeared, the sky glows with a deep, burning amber. It is the color of heated metal, of forged fire, of something primal and powerful. This is the light that has traveled through the densest air, losing almost everything except its longest wavelengths. Above this amber band, the sky shifts to orange, then to pink, then to the deep violets that dominate the upper sky. These colors blend seamlessly into each other, creating gradients that no painter could replicate. The transitions are smooth, gradual, infinite in their subtlety. The clouds that catch this light become characters in the drama. High-altitude clouds, composed of ice crystals, glow with pink and magenta light. Lower clouds, thicker and more substantial, are painted in deeper oranges and reds. Their edges catch the light first, becoming bright against the darker cloud bodies, creating a three-dimensional effect that adds depth to the scene. You notice that the colors are not uniform across the sky. They are brightest in the west, directly above where the sun set, and fade gradually toward the east. The eastern sky is still dark, approaching night, while the western sky blazes with the last light of day. This gradient is a measure of how much atmosphere the light has passed through. The farther from the sun's setting point, the shorter the path through the atmosphere, and the less dramatic the color transformation. The deep violets at the zenith are particularly fascinating. These colors come from sunlight that is illuminating the upper atmosphere from below the horizon. The light must travel through even more atmosphere to reach these heights, but it does so at a different angle, interacting with the thin air of the upper atmosphere in ways that produce violet hues. This is why the zenith can appear purple even when the horizon is orange and red. You think about the physics behind each color. The amber light reaching you now has survived an atmospheric journey of over 300 kilometers. In that distance, it has encountered billions of air molecules, each one a potential obstacle. But because of its long wavelength, it has slipped through with minimal interaction, preserving its energy and direction. The red light has done even better. With its wavelength of 700 nanometers, it is almost twice as long as blue light and scatters only about 1/10 as much. This is why red light can be seen even after the sun has fully set, illuminating clouds from below and creating the afterglow that can last for an hour or more. As the sun continues to drop below the horizon, the colors begin their slow fade. The ambers near the horizon deepen to red, then to a deep crimson, then to a dark purple that is almost indistinguishable from night. The violets at the zenith follow a similar progression, fading gradually as the light source moves farther below the horizon. This fading is itself a product of scattering. Even the long wavelength red light will eventually be scattered or absorbed if it travels through enough atmosphere. As the sun drops lower, the path length increases and even the reds begin to fade. The last color to disappear is usually a deep crimson or purple, the final gasp of the day's light. You watch as this final color fades slowly, imperceptibly, until the western sky is the same deep blue as the rest of the dome. The transition is so gradual that you cannot pinpoint the moment when color becomes darkness. One moment the sky is purple, the next it is night. The stars emerge more brightly now, their light unaffected by the sunset colors. They have been there all along, of course, but the bright sky hid them from view. Now, with the last traces of sunlight gone, they reveal themselves in all their glory. You think about the journey of the light you have just witnessed. Each photon that reached your eyes traveled 93 million miles from the sun, then took a detour through Earth's atmosphere, bouncing and scattering, losing energy and wavelength until finally, as a deep red or violet survivor, it completed its journey in your retina. You have seen the end of an 8-minute journey, the final destination of particles of light that began their existence in the nuclear furnace of the sun. The deep violets and burning ambers are gone now, but their memory remains. You carry with you the image of the sky at its most dramatic, painted in colors that no artist could reproduce, created by physics that no human could improve upon. This is the climax of the sunset. This is the moment when the surviving photons make their final stand. This is the deep violets and burning ambers that mark the transition from day to night. The night deepens around you, and you turn away from the western horizon. Behind you, the sky is dark, but you know that somewhere beyond the curve of the earth, The sun is still shining, still sending its light on that 8-minute journey. And tomorrow that light will create another sunset, another display of deep violets and burning ambers, another demonstration of the gentle science that paints our sky. You walk into the night carrying the colors with you. You stand in the deepening twilight, watching as the last traces of color fade from the western sky. But even as the vibrant hues disappear, something subtle and beautiful continues to happen. The light that remains does not simply stop. It curves, bends, follows the very curvature of the earth itself. This is the final act of atmospheric refraction, the gentle bending that allows light to reach you even after the sun has long since set. To understand this phenomenon, you must first understand that light does not always travel in straight lines. In a uniform medium it does. But Earth's atmosphere is not uniform. It is a layered envelope of gas, each layer with slightly different density and temperature. As light passes through these layers, it bends gradually, following a curved path that mirrors the curve of the planet itself. Imagine a runner trying to run along a beach at the edge of the sea. The sand near the water is firm and compact, allowing fast running. Higher up the beach, the sand is soft and loose, slowing the runner down. If the runner stays exactly at the water's edge, they run straight. But if they drift slightly higher into the soft sand, they slow down. If they drift lower into the harder sand, they speed up. The result is a curved path, bending toward the slower medium. Light does the same thing in the atmosphere. The lower layers of air are denser, slowing light down. The upper layers are thinner, allowing light to travel faster. When light enters the atmosphere at an angle, the part of the wavefront that enters the denser lower air slows down while the part in the thinner upper air continues at speed. This differential speed causes the light to bend, curving toward the denser air. As the sun sets below the horizon, its light continues to reach you because it is curving along with the earth. The photons do not travel in straight lines from the sun to your eyes. They follow a curved path, bending gradually as they pass through layer after layer of atmosphere, following the very curve of the planet. You can see the evidence of this curving in the duration of twilight itself. If light traveled in straight lines, the moment the sun dipped below the horizon would be the moment darkness began. But twilight lasts much longer, up to an hour or more, because the curving light continues to illuminate the sky long after the sun has physically set. This curving is not uniform. It depends on the angle of the light and the density of the atmosphere. Light that enters the atmosphere at a shallow angle, as it does at sunset, bends more than light entering at a steep angle. This is why the setting sun appears flattened. The bottom edge, where light bends more, is lifted more than the top edge, compressing the image vertically. The curving also depends on atmospheric conditions. Temperature inversions, where warm air sits above cold air, can create unusual bending patterns. In some conditions, light can be bent so much that it appears to come from below the horizon, creating mirages of distant objects. In the Arctic, this effect can make the sun appear to rise days before it actually does, a phenomenon that has fooled explorers for centuries. You watch as the last light fades, but you know that photons are still curving over the horizon, still making their way to your eyes. The light that reaches you now has traveled a path that is not straight but curved, bending through layer after layer of atmosphere, following the gentle arc of the earth itself. This curving has a softening effect on the remaining light. The hard edges of the day are gone, replaced by the velvety tones of twilight. The light is diffuse, scattered, bent, no longer direct and harsh but indirect and gentle. It wraps around objects, softening their outlines, creating a world without sharp shadows or bright highlights. You look at the landscape around you and see this softening in action. Trees that were sharply outlined against the bright sky are now soft silhouettes, their edges blurred by the bending light. Hills that were distinct are now merging with the sky, their forms dissolving into the twilight. The world is becoming less distinct, more dreamlike, as the curved light loses its power to define sharp boundaries. The colors of twilight are also affected by this curving. As light bends through the atmosphere, different wavelengths bend by different amounts. Blue light, with its shorter wavelength, bends more than red light. This differential bending, called dispersion, can create subtle color fringes at the edges of objects, adding to the velvety quality of the twilight light. You notice these fringes if you look carefully. The edges of clouds against the darkening sky may show a faint blue or purple tint where the shorter wavelengths are bent more sharply. The horizon itself may have a thin band of green or turquoise, the last remnants of the colors that have been scattered and bent through the atmosphere. The physics of this curving is described by Snell's law, named after the Dutch mathematician Willebroord Snellius, who discovered it in 1621. Snell's law relates the angle of incidence to the angle of refraction based on the refractive indices of the two media. In the atmosphere, with its continuously varying density, the application of Snell's law becomes complex, requiring integration along the entire path of the light. But you do not need mathematics to appreciate the effect. You can see it with your own eyes, feel it in the quality of the light, experience it in the lengthening of twilight. The photons curving over the horizon are not just a theoretical concept. They are a visible reality, a daily demonstration of the wave nature of light and the complexity of the atmosphere. As the twilight deepens, the curving becomes more pronounced. The light that reaches you now has traveled the longest path, bending the most, coming from farthest below the horizon. This light is the oldest, having left the sun more than 8 minutes ago and spent additional minutes curving through the atmosphere. It is light that has worked hard to reach you, fighting against gravity and density, bending and twisting to make its final delivery. You think about the journey of these photons. They began in the nuclear furnace of the sun, took 8 minutes to cross the vacuum of space, then encountered Earth's atmosphere and began their slow, curved descent. They passed through layers of air, each one bending them slightly, until finally, after traveling hundreds of miles through the atmosphere, they reached your eyes at the exact moment you were looking. This is the gift of atmospheric refraction. It extends the day, softens the light, creates the velvety tones of twilight. Without it, the transition from day to night would be abrupt and harsh, a sudden switch from light to dark. With it, the transition is gradual, gentle, beautiful. The last photons are reaching you now, their path so curved that they are coming from far below the horizon. They carry with them the memory of the sun, the warmth of the day, the colors of the sky. They are the final messengers, the last deliverers of daylight. You watch as they fade, as the curving light finally gives way to true darkness. The stars emerge more brightly now, their light also curved by the atmosphere, though their distance makes the effect less noticeable. The Milky Way appears, a river of stars that has been there all along but was hidden by the brighter sky. You stand there at the threshold of night, and you understand. The light that curved over the horizon to reach you is the same light that will curve over the opposite horizon tomorrow morning, bringing the dawn. The cycle continues, the bending never stops, the photons always find a way. The night is fully dark now, but you carry with you the memory of the curving light. You have seen photons follow the curve of the earth, bending through the atmosphere to deliver their final message. You have witnessed the gentle science of refraction at its most elegant, its most beautiful. This is the curving of photons over the horizon. This is the velvet tones of twilight. This is the final gift of the setting sun. You stand at the final threshold, where the last traces of daylight yield to the embrace of night. The sky above you is a deep, dark blue, almost black, with only a faint glow on the western horizon marking where the sun has set. The stars are out in full force now, their ancient light having traveled years, centuries, millennia to reach your eyes. And yet, even now, even in this darkness, the physics of the sunset continues to operate, continues to shape your experience of the fading day. What you have witnessed over the past hours is not merely a sequence of beautiful colors. It is a demonstration of fundamental physical principles that govern the interaction between light and matter. Refraction bent the sun's image, lifting it above the horizon after it had physically set. Scattering removed the shorter wavelengths, stripping away the blues and leaving behind the warm tones of sunset. Dispersion created the deep violets and burning ambers, painting the sky in colors that seem almost supernatural. And refraction again curved the photons over the horizon, extending the day and creating the velvety tones of twilight. Each of these phenomena is described by precise mathematical laws. Snell's law governs the refraction, with its elegant relationship between angles and refractive indices. Rayleigh's scattering equations predict exactly how much light of each wavelength will be scattered by air molecules. The dispersion of light through the atmosphere follows principles that have been understood since Newton first passed sunlight through a prism. But standing here, watching the last light fade, you realize that the mathematics, while beautiful in its own way, does not capture the full experience. There is something more happening here, something that transcends the equations. The physics creates the conditions for beauty, but it does not explain why that beauty moves you, why it stirs something deep within your soul. This is the intersection of physics and the fading day. This is where objective science meets subjective experience, where measurable phenomena give rise to ineffable emotion. The photons that reach your eyes are real, their wavelengths measurable, their paths calculable. But the feeling they evoke, the peace, the wonder, the sense of connection to something larger than yourself, that cannot be measured or calculated. It can only be experienced. You think about the countless humans who have watched sunsets before you. For most of human history, they did not understand the physics behind what they were seeing. They did not know about refraction or scattering or dispersion. They saw the sun disappear below the horizon and the sky turn colors, and they created stories to explain it. Gods crossing the sky, celestial chariots, dying and reborn deities. Now you know the science. You understand why the sun appears flattened, why the sky turns orange, why the twilight lingers. And yet, knowing does not diminish the experience. If anything, it enhances it. The physics adds a layer of appreciation, a deeper understanding of the forces at work. The beauty is not lessened by being understood, it is amplified. The last glow on the horizon is fading now, a thin band of deep orange that marks the final resting place of the day's light. In minutes, it too will be gone and the sky will be uniformly dark. But even as it fades, you know that the physics continues. Somewhere beyond the horizon, the sun is still shining, its light still traveling, still bending, still scattering. The cycle continues as it has for billions of years, as it will for billions more. You think about the relationship between light and time. The sunlight that reached you during this sunset left the sun 8 minutes ago. In those 8 minutes, it traveled 93 million miles across the solar system. During that journey, it was pure potential, carrying all the colors of the spectrum within it. Only when it encountered Earth's atmosphere did it reveal its true nature, separating into the components that painted the sky. In a sense, you have been watching history. The light you saw was created in the sun's core hundreds of thousands of years ago, then took 8 minutes to cross space, then spent additional minutes curving through the atmosphere. The photons that reached your eyes were ancient travelers, carrying with them the story of their long journey. The temperature is dropping now, the air cooling rapidly without the sun's warmth. You feel it on your skin, a gentle chill that reminds you of the day's end. The sounds of the world are changing too. The birds have stopped singing, the insects have begun their nightly chorus, the distant hum of human activity has faded. The world is settling into night. This too is part of the intersection. The same sun that painted the sky provided the warmth that sustained the day. Its absence brings cold and darkness, but also the peace of night, the opportunity for rest, the promise of renewal. The cycle of day and night is as fundamental as the physics that creates it. You look up at the stars, those distant suns whose light has traveled for years to reach you. Their light too is affected by the atmosphere, twinkling as turbulence in the air bends it slightly. This twinkling, called scintillation, is another form of atmospheric refraction, another demonstration of the same principles that gave you the sunset. The stars are steady, but the atmosphere makes them dance. The Milky Way stretches across the sky, a river of light that is actually the combined glow of billions of stars. Its light has traveled thousands of years to reach you, passing through interstellar space, through the solar system, through Earth's atmosphere, finally bending slightly to enter your eyes. You are seeing the galaxy from the inside, a perspective that is only possible because you are part of it. You think about your place in all of this. You are a conscious being, capable of understanding the physics that creates the sunset, capable of feeling the emotions it evokes. You are made of atoms that were forged in stars, that have been part of this universe since its beginning. The same carbon that forms your body was created in stellar fusion billions of years ago. The same oxygen you breathe was produced by ancient stars and scattered across space. You are literally stardust, and you are watching starlight interact with the atmosphere of your planet. This is the deepest intersection, the realization that you are not separate from the physics you observe. You are part of it. The light that enters your eyes triggers chemical reactions in your retina, sends electrical signals through your optic nerve, creates patterns of activity in your brain. The experience of beauty is itself a physical process, as real as the refraction that bent the light. And yet, the experience transcends the physical. The awe you feel, the peace, the sense of connection, these are not reducible to neural firing patterns. They are emergent properties of a conscious mind, products of a brain complex enough to reflect on its own existence. The sunset is beautiful not just because of physics, but because you are here to witness it, to feel it, to be moved by it. The last trace of color is gone now. The western horizon is as dark as the rest of the sky. The night has fully arrived with all its stars and mysteries. You stand in the darkness, but you are not afraid. The darkness is not an absence. It is a presence, a different kind of light, a different kind of beauty. You think about the phrase that came to you earlier, the intersection of physics and the fading day. This is it. This is the moment when science and experience meet, when understanding and feeling become one. The sunset was physics in action, but it was also poetry, art, spirituality. It was both at once, inseparable, unified. You turn away from the western horizon, ready to embrace the night. The day is over, but its memory remains. The physics continues as it always does, but for now you are done with physics. For now there is only the night and the stars and the peace that comes with darkness. The intersection has been crossed. The day has faded. The night has come. You walk into the darkness, carrying with you the memory of the sunset, the understanding of the physics, and the peace that comes from witnessing something beautiful. The photons that painted the sky are gone now, scattered into the universe, but their image remains in your mind, a permanent record of this intersection of physics and the fading day. This is the final lesson of the sunset, that science and beauty are not opposites, but partners. That understanding does not diminish wonder, but deepens it. That the most profound experiences come when we recognize our place in the physical universe while also honoring the subjective experience that makes us human. The night surrounds you, dark and peaceful. Somewhere beyond the horizon, the sun is beginning its journey toward the opposite side of the world, where it will soon rise and paint another sky with color. The cycle continues as it always has, as it always will. And somewhere, someone will watch that sunrise, experiencing their own intersection of physics and the fading or dawning day. You are part of that cycle now. You have witnessed the sunset, understood its physics, felt its beauty. You carry that experience with you, a permanent part of who you are. The stars shine down on you, their ancient light a reminder of the vastness of the universe and your small but significant place within it. You are made of stardust, watching starlight, understanding the physics that connects you to everything else. This is the intersection. This is the fading day. This is the peace that comes at the end.